Good day, stat students. So today we're going to talk about section 3.4, and there's some cautions in using correlation and regression analysis. The good thing is that we've already talked about a couple of these. So for instance, outliers. We've talked about how outliers goes ahead and would change the value of the correlation coefficient. And also, if you had outliers in your data, it also would shift the sample regression line. Okay. And so outliers, you got to pay attention to them too. Don't extrapolate. So do not take your line and just simply extend it out past the minimum and maximum values of x, because we don't know what happens out there. And then 3, we haven't talked about this, is that a strong correlation does not imply x causes y. And so often the way you'll hear this is that correlation does not imply causation. And I kind of expanded that to just give you the sentence here. So a strong correlation does not imply x causes y. So let me give you a silly example, but I think it's pretty effective. And it really is truly silly. And so let's take a look at monthly suntan lotion sales and make that x, and let's make y monthly shark attacks. So if you go to a region that has like a beach, okay, that is, and the beach has an ocean with it, that believe it or not, if you look in the monthly suntan lotion sales in that area, and then you take a look at monthly shark attacks, that there is a strong correlation between these two. All right, and so well, let's think about this for a second. Are we saying then that as we buy more suntan lotion, that all of a sudden the sharks are going to get more attracted to us in some way and bite us more, and there's going to be more shark attacks, and it's going to be a Sharknado type deal that they're going to jump out of the water and start eating us and stuff like that? I don't think so. Okay, I don't think that's the case. All right, and so what are we saying? What we are saying is that somehow mathematically x is connected to y. All right, mathematically. And this may sound a little strange, but so what our model could do is that as the suntan lotion sales changes, we might have a pretty good idea how monthly shark attacks are going to change also. All right. So we could go ahead and predict values for y using x, but use a heck of a lot of caution before you say that x is causing y. All right. We're going to find out in chapter 4 when we can say that one is causing the other one. But if, in general, okay, if you just pull these numbers, out of some sort of database and you say, oh, look at this, and they're highly correlated, well, use caution before you say that one is causing the other one, all right? So you'll see in chapter 4 when we can do that, all right? So what is going on here? Well, in my opinion, there's another variable that's connecting suntan lotion sales and shark attacks on a monthly basis. And to me, it is temperature. All right. So as temperature starts to increase, so the ambient temperature starts to increase, we tend to want to go outside, and people who live by a beach that's by an ocean, they like to go to the beach and do those things, right? And so they're going to buy more suntan lotion, right? But as the ambient temperature rises, the water temperature also rises. And as the water temperature also rises, the fish go, ooh, so it's warmer water, so I'm going to swim over here. Well, what's going to follow it? It's the sharks, right? And so the shark's going to follow its food source. And so then all of a sudden, humans and sharks are coming in more contact with each other. And so that's my simplistic view of things. Maybe a marine biologist would say there's other variables on top of this that also causes it, but for this simple demonstration, example, we'll just say that temperature is the one thing that's linking these two things. All right. So we have a name for temperature, and the name that we give the temperature is what we call a lurking variable. All right. Lurking variable. So a lurking variable is a variable that is usually not observed, but it's there. Okay, so we know that temperature is in the background. Okay, but it's not really needed to be measured. Okay, and put into the model based upon what we have to do. All right, and so this is a variable that is usually not observed that influences the association between the variables of interest. Okay, And so lurking variables can be a problem, all right? But you can, what you're going to find out in Chapter 4 is that we mitigate their influence quite a bit, okay? And you'll see why. Now, if you have more interest in this topic, you can also take a look at what's called confounding variables. Those are variables that we actually do measure, and so we know they're there. Now we're going to measure them, and we want to see what kind of influence that they have on the variables, but they're being measured, okay? If you want to take it even a step further, you can take a look at what's called Simpson's paradox. Okay? And so, anyways, that's the end of this section. Do you need to know these things here? No, you don't have to look them up if you don't want to. All right, but certainly know lurking variables and the cautions in using correlation and regression, and certainly know the idea that just because there's a strong correlation between X and Y, that does not imply that X is causing Y. Thank you for your time.